Eutrophication is the process by which water bodies become degraded and eventually so contaminated with toxic cyanobacteria that the water is unusable for recreation, irrigation, or drinking. The term eutrophication comes from Greek and means well-nourished. So understanding eutrophication is about understanding the nutrient cycle and how the misappropriation of nutrients leads to toxic cyanobacteria becoming so well-nourished that they completely dominate the water body. It's important to understand that eutrophication is a systemic process. It affects the whole water body. You can't have eutrophication in one area of a lake only, and equally, you can't just treat or remediate one area of a lake either. Because eutrophication is systemic, it operates according to the laws of systems theory, which means that eutrophication is a multifaceted reorganization of a whole biome with many factors at play. This produces a plethora of symptoms, and these symptoms often show some correlation that people too easily confuse as causation. Because it's systems-based, there's feedback and interaction between the causative factors and the symptoms, making it much more complex than simple cause and effect. To understand the process, let's break it down into physical changes and biological changes. The main physical changes that occur as eutrophication takes place are firstly stratification of the water column, which manifests in two ways. The basic laws of physics tell us that warmer water is less dense than cold water. So warm water rises to the top and denser cold water sinks to the bottom. Oxygenated water is less dense than deoxygenated water. So oxygenated water rises to the top and denser deoxygenated water sinks to the bottom. Stratification or layering takes place in a eutrophic water body so that at the bottom you have dense, heavy, colder deoxygenated water. Because this water is denser and heavier, it's effectively locked in at the bottom of the water column by gravity, making it very difficult to reverse. Deoxygenation of the water has major consequences because deoxygenation causes what are called anaerobic conditions. Living organisms can be broken down into two types: aerobic ones that need oxygen and anaerobic ones that don't. Anaerobic conditions obviously favor anaerobes. Weeds, algae, and cyanobacteria are anaerobes, so this is good news for them. But fish need oxygen in the water to breathe, so it's bad news for fish. The third significant physical change that takes place is an accumulation of organic sediment in this anaerobic benthic zone at the bottom of the water column. This organic sediment is rich in nutrients, so any organisms that can exploit these conditions and access those nutrients will be well nourished in eutrophic conditions. Now let's look at the biological changes that take place. The first point to note is that eutrophic conditions are less favorable to oxygen breathers or animal life and more favorable for plant life, such as aquatic weeds, algae, and cyanobacteria that don't need oxygen. Floating aquatic weeds and algae can take up nutrients, most importantly nitrogen and phosphorus, that are dissolved in the water column. For rooted aquatic weeds, a nutrient-rich sediment provides a perfect rooting bed for them to flourish. But over time, it's the potentially toxic cyanobacteria or blue-green algae that best exploit eutrophication to their advantage. Nutrients such as nitrogen and phosphorus are taken up by aquatic weeds and algae during the summer months as they bloom and flourish. In winter, they die off and sink to the bottom and decompose. This decomposition makes the nutrients available again in the sediment for next year's summer blooms. In addition to this, you get other life forms dying off, leaves from trees and other organic inputs that add to the nutritious sediment. So recycling of nutrients occurs as positive feedback loops drive worsening algae blooms and then cyanobacteria blooms annually, as eutrophication itself is worsened by similar positive feedback loops. So biologically, what we see is conditions that favor nutrient appropriation in favor of life forms that we do not want in our water. Algae and toxic cyanobacteria are the ones that become well nourished in a eutrophic water body. To understand what cyanobacteria are and where they came from, we need to go back to when the very first life forms emerged on Earth. Because there had never been any living thing on Earth, there was no food as such. So the very first life forms were autotrophic bacteria, meaning that they had to be able to create their own nutrition from scratch. Conditions are harsh, and the raw materials that they had to work with were substances that are toxic to us, such as hydrogen sulfide, ammonia, and methane. These extreme conditions only suit extremophiles. Such organisms still proliferate where such extreme conditions still exist, like at the bottom of the ocean, where sulfurous material leaks through the Earth's core. The thing is, to do the chemical processing for biomass formation on a diet of hydrogen sulfide, ammonia, and methane takes a lot of chemical energy and is very inefficient. So organisms evolved that could harness the energy in sunlight to fuel their biomass formation and give them a competitive advantage over the extremophiles. These organisms are what we call cyanobacteria or blue-green algae. Cyanobacteria are extremely resilient, agile, and adaptable. So they produced biomass prodigiously and became by far the most dominant life form on Earth for hundreds of millions, if not billions of years. But here's the thing. Photosynthesis doesn't need oxygen as an input, but it produces oxygen as an output. So cyanobacteria emitted huge amounts of oxygen into the atmosphere, fundamentally changing it. This oxygen first produced carbon dioxide in the atmosphere. Algae evolved and began to beat out and dominate cyanobacteria because they could use carbon dioxide as a carbon source for biomass formation by photosynthesis. With cyanobacteria and algae both producing oxygen as a byproduct of photosynthesis, the atmosphere became plentiful in oxygen, or aerobic, and this created an environment that favored aerobic organisms, and they, the animal kingdom, began to evolve and proliferate to the detriment of cyanobacteria. And here we are, the dominant species on Earth, because cyanobacteria were the first organisms to bring about their own demise by emitting gas into the atmosphere. But cyanobacteria haven't gone extinct. They're still around and making a comeback in our water resources everywhere. So let's understand how eutrophic conditions favor cyanobacteria. Cyanobacteria thrived in primordial soup, which is an aquatic environment in which there's little to no oxygen, and nutrients are available in the form of substances such as hydrogen sulfide, ammonia, and methane. Where do they find these conditions nowadays? We're creating them at the bottom of eutrophic water bodies. Did you know that recent research indicates that 20% of the methane emitted into the atmosphere does not come from hydrocarbon combustion, but from the sediments at the bottom of eutrophic water bodies? So how are cyanobacteria able to exploit eutrophic conditions and appropriate nutrients to outcompete other life forms and proliferate so prodigiously? The three facts about a eutrophic water body that you need to understand. Cyanobacteria need to be at the surface in order to hog the sunlight to photosynthesize and proliferate. Cyanobacteria need to be at the bottom to take advantage of all the nutrients that are available in the primordial soup conditions where they can assimilate them, but competitors can't. And a eutrophic water body is stratified into layers. The fourth thing you need to know is that cyanobacteria have tiny gas vesicles in their cells, and they can inflate and deflate to control their buoyancy. In a stratified water column, where the density of the water varies with each layer, if you can control your buoyancy by inflating and deflating gas vesicles, you can descend to the bottom at night, load up on nutrients, and then float back up to the top during the day to hog the sunlight and convert all those nutrients into new biomass as you rapidly proliferate and bloom by outcompeting your competitors for nutrients and the sun's energies. That's exactly what cyanobacteria do. So by causing eutrophication, we're turning the clock back billions of years, recreating primordial soup conditions and actively promoting the proliferation of potentially toxic cyanobacteria that degrade our water resources. Most interventions that claim to be solutions to eutrophication fail because they do not understand the process of eutrophication or the rules of system theory that are at play. So they focus on fighting symptoms, not causes. Let's look at a few of these solutions to understand why we can predict beforehand that they will fail and therefore don't need to waste money proving this to ourselves. Herbicides kill off weeds that fall to the bottom where they decompose and release nitrogen and phosphorus that nourishes future aquatic weed and algae growth. This is a great business model for the herbicide companies because they're going to be paid to come back next year and repeat the process. Algicides kill off algae that fall to the bottom where they decompose to release nitrogen and phosphorus that nourishes future aquatic weed and algae growth. This is a great business model for the algicide companies because they're going to be paid again next year to come back and repeat the process. Lots of phosphorus in the water column nourishes weed, algae, and cyanobacteria growth. So let's reduce phosphorus in the water column. Theoretically, there are two ways to do this. If we raise dissolved oxygen levels in the water, this causes phosphorus to precipitate out and fall into the sediment. So that will starve the algae of nutrients, right? Well, yes, but when you precipitate the phosphorus into the sediment, who's going to benefit from this concentrated nourishment? Well, that would be the rooted weeds and the cyanobacteria. So expect to see more of them, and we do. Chemical precipitation of phosphorus is just another way of achieving the same thing, using chemicals such as alum. This has been a favored practice in the USA for many years, and it's a contributing factor in the worsening of eutrophication and toxic cyanobacteria blooms in the USA. Reducing phosphorus inflows is closing the stable door after the horse has bolted, because what is already there is being recycled. However well-intended and effective the strategy might be, all it can do is slow down the rate of future eutrophication. It can never stop it or reverse it. In addition to these, there are contraptions that aim to stir up and create movement in the water because algae like stagnant water. And even better, they can be solar powered. They're just gimmicks. All these solutions suffer from the same failing. They're not developed with a sound understanding of the systemic nature of eutrophication. They focus on a single symptom and ignore the feedback and interactions between the causative factors and the symptoms. So they are no more than attempts to shuffle the deck chairs around on the Titanic. And they just set up a game of whack-a-mole, where whatever intervention you do here causes another problem there. This is often a great business model for the solution providers, but it doesn't do anything to reverse eutrophication or restore water quality. So how would you verify that someone who claims to have a solution to eutrophication and toxic cyanobacteria blooms is telling the truth? What do you need to look for? In essence, you want to see three things. Firstly, physical changes that will negate the competitive advantages that cyanobacteria have in eutrophic conditions. Secondly, the promotion of catabolic metabolism. This breaks down organic contaminants to mobilize nutrients so they're available to be taken up in the formation of desirable biomass, such as zooplankton and fish. And lastly, the promotion of anabolic metabolism, to actively support the uptake of these nutrients by organisms that create the foundations of a productive food chain. A robust, biodiverse food chain ensures a sustainable way that cyanobacteria are denied the nutrients they need. But most importantly, you'd want to ensure that the solution is a holistic one that operates in a systemic, synergistic manner and sets up feedback effects to our advantage by establishing feedback loops that strengthen and entrench the conditions we want to prevail to ensure sustainability of the solution. So the evidence that you would want to see of the Eutrophy solution in action would be a logical demonstration of success in achieving destratification of the water column to negate the advantages that cyanobacteria have by being able to navigate up and down a stratified water column. Reoxygenation of the benthic zone at the bottom of the water column in favor of aerobic and not anaerobic life forms. Reduction in nitrogen and phosphorus levels in the water column and in the sediment. Reduction in muck and sediment itself. Reduction in the proliferation of aquatic weeds, algae, cyanobacteria, and pathogenic anaerobes such as E. coli. Assimilation of the nutrients into a productive food chain that would be evidenced by improved fish life and improved biodiversity. The easiest way to check out the effectiveness of the Eutrophy solution in action is to go like this.